Yes. Okay, looks good.
Okay. So you see my presentation? Okay, excellent.
Yeah, this is full screen.
Tell me when I start then.
Okay, please.
Okay, should I? Well, thank you for inviting me again, Andres. It's always a pleasure. This is a class that I have done last year, and it's not that easy because it's an advanced part of CROCO, the non-adversarial solver and non-adversarial simulations. So it is interesting, but not always very easy to explain in simple terms. So it's an effort, but it's, I think, very interesting effort for me to do. And I will try to make it interesting and informative. Though if you don't understand everything I will say, don't be worried. You can always try to complement some of the things that I will say somewhere else. I hope that you just get maybe the essential part of it and the idea behind why we are doing these developments, besides having fun doing it. So this is the plan for the next 2 hours, I think, or so. First, I will start with an introduction of the subject of non-adversarial problems, and then I will go for the non-adversarial equations, what they are, what they represent, what are the assumptions behind it, and then the non-adversarial solver in CROCO that has been developed to solve the equations. This is the non-easy part, I would say. We'll go slowly, and if some things will be more difficult to understand than others. Then I will follow with applications, some basic applications that will show how it works, some validations maybe that you can do after. And then we will stop here for a little break, maybe 5 minutes, I don't know. And we'll come back for a second part that will be a particular application on surface gravity waves, which are particularly interesting with the non-aerostatic model and nearshore dynamics. Then I will say a few words on numerical methods, because I think it is important and not it's not always presented, these aspects of numerical methods on the quality of the results that we are getting with models. So we'll say a few words about this, particularly in the context of the non-aerostatic model and the solving of. Okay, so let's start with an introduction of subject. This is a simulation that was not done with CROCO, but could have been. And it shows convection of fluid. At the surface, it is heated, and at the bottom, it is cooled. So it is typically a non-adversarial regime of circulation that is convection. Typically non-adversarial, because in the adversarial assumption, the gravity and the pressure gradient compensate each other, and they are in equilibrium. It is the Archimedes balance. And with convection, it is the opposite, because the pressure gradient goes with the gravity, and then there is an instability that develops and creates movements that can be very strong. So this is typically non-adversarial, but it's not the only non-adversarial type of regime, flow regime, and we will see what we can expect in the full range of oceanographic scales in terms of non-hydrostatic regime. Maybe one way to look at that is to draw a schematic view of the scales of the ocean and the various processes that we expect along these scales, from the mesoscale all the way down to the dissipation scale to the right. So the mesoscale of the ocean is where most of the energy in the ocean resides. And we have been studying this mesoscale for a very long time because it is important in the general circulation. And CROCO, like many other models, have been developed at the beginning to solve these mesoscales very well, in particular with respect to the coast, when they interact with the coast. But soon we realized that there are a number of scales below with important processes that needs to be also modeled in order to get a better picture of what's going on near the coast in particular, but also offshore. And like in the last 20 years, we've been studying some mesoscales instantly, all the way to resolutions of 1 kilometer. And below is a simulation giving an example of what CROCO has been doing in this kind of scales. So this is something we know how to do very well. But again, a new challenge is to go further into scales that were maybe not that interesting, but we now realize that a good knowledge of these scales is important when we want to understand the interaction between the large scales and the small scales, and how the flow behaves. So starting with internal waves and heterostrophic instabilities, we slowly go to processes where the flow structure is three-dimensional. So we start in the quasi-geostrophic zone where Coriolis force is important, and the horizontal scales are much more important than the vertical scales. And slowly we go towards scales where horizontal and vertical scales are very similar. And that's where the non-hydrostatic regime begins. It is about 100-meter scale and all the way down to the dissipation scales. At some point in the inertial zone, there are not very strong instabilities that produce energy, and we just have a sort of cascade of eddies towards the smaller and smaller scales. And we call that the large eddy simulation zone. That's an area around 1 centimeter scale and resolution, I mean. And it is quite difficult to get there because the resolution is very small. But most of the time, we will be in the zone between 100 meters and this area. Okay. So how do we get there? First of all, we need equations that are non-hydrostatic. So what are they? They are basically the Navier-Stokes equations, which means compressible non-hydrostatic equations, which are presented here. The three first are the momentum equations for the three components, U and V on the horizontal and W in the vertical. You see the time evolution term, then a term of acceleration, of advection, and then Coriolis terms and pressure gradient. And this is the same terms that you see for all components. For Coriolis parameter, maybe one word, you see on the right a schematic of the rotation of the Earth that gives two components at any latitude. This is because the rotation is oriented that way, along the North Pole. One component is vertical, that is perpendicular to the surface of the Earth, and one component is parallel. This component is supposed to be the most important for ocean circulation, but the parallel component becomes more and more important as we get to the equator. And near the equator, it can play a role. So we leave it here, and we call the Coriolis parameter associated with this component Fy, while the more usual vertical component is called Fz. So we have the two components here, and we have one component Fy in the vertical equation as well. The fourth equation is a continuity or mass balance equation that conserves the mass as opposed to the momentum. And with these four equations, we have a system of equations called the Navier-Stokes equations. This is the start. We can write these equations here in a dimensionless system because it will then be useful to understand how we can simplify the equations and remove the non-hydrostatic part in particular. So if we use L as a horizontal scale and H as vertical scale, we have an aspect ratio, delta, which is H over L. And then we can rewrite the equations with dimensionless variables. I get rid of the primes in order to make the equations more easy to read, but these are dimensionless equations. In these equations, there are terms that have factor delta, which is interesting for us. One in front of the non-traditional Coriolis parameter that I mentioned before, and also, and here also in the vertical equation, and we have delta square that is even stronger in front of the acceleration for the vertical equation. And the two terms that are on the right here are the hydrostatic terms, the balance between vertical pressure gradient and gravity. So the first thing that, the first approximation hypothesis that we can do as we proceed towards simplification is to get rid not of the delta terms, but we can make the Boussinesq hypothesis, which means that the small, which is true. And in this case, the term that tell us that about the variation of density in time becomes very small, and we only keep a divergence term, a non-divergent term. So the Boussinesq hypothesis on a row gives us an incompressible set of equations. So these are not anymore the compressible non-hydrostatic equations, but the incompressible non-hydrostatic equations. And for the ocean, people have used essentially these sets of equations for the very small scales. So the next step, going to larger scales, will be to consider delta to be much lower than 1, meaning that the vertical scale becomes much lower than the horizontal scale. So this is an hypothesis, again, that we can make when we consider larger scales. So the first term that will go in this case will be the delta square term, which is the acceleration of W. So we don't have yet hydrostatic equations because we still have this non-traditional term. And the the non-traditional Coriolis term can still be relatively large, not dominant compared to the hydrostatic terms, but relatively large near the equator, but near the equator only. So for problems, large-scale problems near the equator, this set of equations that are called the quasi-hydrostatic equations can be used with good benefit, although a lot of people tend to neglect the non-traditional Coriolis terms at the equator also. Then the last assumption that we make is that these terms are not important enough to consider, and then in this case, we have the the most used equations for the ocean that are the hydrostatic equations. Sometimes we call them the primitive equations. So that was a way to show how the non-hydrostatic equations are represented in the terms of the Navier-Stokes equations, and the parameter delta is a crucial parameter for this assumption. Now that we have the non-hydrostatic equations and we understand where are the important parameters, we need to solve these equations numerically, because of course we cannot solve them mathematically. One is the pressure correction method that is used for incompressible equations. And most models use this method for the ocean, not for the atmosphere, but for the ocean. The second method, which is used a lot in the atmosphere, is the time-splitting method, which is used for compressible equations. And CROCO is at the moment the only ocean model that propose this type of approach. Actually, we have both approaches for CROCO. The pressure correction method is proposed in a version of CROCO, but not in the distributed version of CROCO. Only the second method is proposed in the distributed version at the moment. The two methods will be proposed at some point. So one way to also look at the difference in the way of solving the equations is to consider the pressure separable between the atmospheric pressure at the surface, the hydrostatic pressure, which is in balance with the gravity, and what is left, that is a non-hydrostatic pressure. The hydrostatic pressure is carried across the domain with gravity waves, similarly to what you see in these animations. Gravity waves